Well, we want to make a very simple analysis, do an air standard analysis. Well, you fix on a fixed amount of air that's trapped in that piston cylinder. We don't have valves letting it come in and out. We make a very simple assumption. And it always stays air. It doesn't turn into CO2 and water vapor, the primary products of burning a hydrocarbon. And it always behaves as an ideal gas. And the combustion process, it's very complicated, but we replace it by just a heat transfer from an external source. And it happens all at top dead center for the Otto cycle. For the diesel, we'll model it where it happens as it starts to expand. There's no intake or exhaust process because it's always air. And that intake and exhaust process is replaced by another heat transfer when it's at bottom dead center. So you have heat rejection when the piston's at bottom dead center. And all of the processes are frictionless, so it's internally reversible. Again, why do we make this? So you can do something, you can make some calculations. Otherwise, the problem's so complex that you can't do anything by hand. You also have the additional cold to describe the air standard analysis. This means everything associated with the air standard analysis, but constant specific heat's evaluated at a low ambient temperature or normal ambient temperature, 25 degrees C or 300 Kelvin. And again, why you do that? Well, it even makes it more doable, and you can glean some insights so that when we analyze the Otto cycle, we can get an analytic expression that says the thermal efficiency of the Otto cycle is 1 minus 1 over the compression ratio to the K minus 1 power. Very simple result. So let's review Otto cycle. So the Otto cycle, we have 4 processes going from state 1 to 2, then 2 to 3, 3 to 4, and 4 to 1. So we talk about the states and the processes between states. And the first process is described as adiabatic compression. So we'll start at a large volume on a PV diagram at state 1, and we'll undergo a compression. That means the volume is going to be decreasing. What's the pressure going to do? It's going to increase as you compress it adiabatically. The temperature will go up too, won't it? So the stroke goes like that. So you stop at some volume here. So this was the volume V1. This is the volume V2. What is the compression ratio? It's defined as the ratio of the volume that you start with divided by the volume at the end of the compression stroke. So this compression ratio is maybe 8, 9, 10, 11. So this is the compression ratio, and they typically are in the range of 10, 9, 11. And you start getting up into the 12, you have to have higher octane, because not only does the pressure goes up so much, the temperature goes up, and it wants to self-ignite. You'll have some knock problems. Process 2 to 3 is constant volume, heat addition. So there's from 2 to 3. And then you have adiabatic expansion again down to 4, and then constant volume heat rejection. How many people recall PV diagram, Otto cycle? No? Well, it's pretty straightforward. This is all adiabatic, so there's no Q. This is all adiabatic, there's no Q. There's heat addition, so Q 2 to 3. And I'm going to show heat addition 4 to 1, but it's a negative heat addition because it's really heat rejection. It's heat coming out. So this is a negative quantity 4 to 1. How about sketch it on a temperature entropy diagram? Well, the process 1 to 2 is straight up. Why? It's constant S. It's internally reversible and adiabatic. So you get from the second law that it's constant S. Then you go along a line of V is equal to a constant specific volume, where you're dumping heat in going up to T3. Then you have constant isentropic expansion from 3 to 4, and then constant volume cooling. There you go, constant volume cooling.
So these are all gases, right? They're outside the
Yes,
dome.
ideal gas only. So if you wanted to try to draw the dome, which I don't encourage you to do, put it way like out of the way. Way down there.
Outside.
Yeah, way far away from the dome. Ideal gas. Yep. Now, if you want to, you can remind yourself Q in from 2 to 3 and Q 4 to 1 is a negative in. Well, we write the first law of thermodynamics for each of the processes from 1 to 2, from 2 to 3, 3 to 4, and 4 to 1. Have I written the first law correctly? Do you understand the notation? Does that look good? So what you want to do is you want to look and say, okay, in the first law for process 1 to 2, are any of the terms 0? Is delta U 0, Q or W 0? The Q, so that's 0. Likewise, process 3 to 4, 0. Now let's look at the process from 2 to 3. Is the Q or any W 0? Is the work 2 to 3 0? And why is the work 2 to 3 0? Constant volume. And we have a closed system, and the only work we have is no shafts or anything. It's just boundary work. And so the integral PDV. And how about 4 to 1? That's 0. So we really have 2 W's and 2 Q's to calculate for the Otto cycle, don't we? I encourage you to go ahead and make a table, maybe a pressure, temperature, and then use for the Otto cycle state 1, state 2, state 3, state 4. And by filling up this table, you'll be able to quickly get work 1 to 2. See, what is work 1 to 2? Just from this equation, you can see I can get work 1 to 2. And then from this equation, I can get Q 2 to 3. And then at the very end, you maybe want to calculate the thermal efficiency for this cycle. What would be the thermal efficiency? It would be the work net work, divided by the Q in, which was 2 to 3. And that work net is simply only work 1 to 2 plus work 3 to 4, because the other two components are 0. I mean, you could put them in the equation. You would put 4 works summing up to get work net, but 2 of them are already 0. So now, as a review, go back and look at and remind yourself about ideal gas models. If you assume constant specific heats, you can get some very simple analytic expressions. For example, the change in internal energy is simply C sub V change in temperature. Thumbs up, you like that? And the change in enthalpy, C sub P change in temperature. True? So don't forget those simple results. Also, the change in entropy can be written like this: C sub P natural log T2 over T1 minus R natural log P2 over P1. Can't rederive that, or I mean I could, but we don't have enough time to redo everything in Thermo 1, but that's one of the major results. How to calculate the change in entropy of an ideal gas. And there it is. It's a function of temperatures as well as pressures. And sometimes students will forget this part, and it's wrong to forget that part. Okay. You also can express it in terms of temperature and volume changes. It's just algebra between these two equations. Okay. But this one is the most common one that if you remember that one, you can do a lot of the calculations. Well, in a minute, we're going to deal with the ideal gas, constant specific heats undergoing an isentropic process. Well, what does it mean by isentropic? That means that change in S is 0, true? So we can take this equation and rewrite it. We can write C sub P natural log of T2 over T1 equal to R natural log of P2 over P1, true? Then we can divide by C sub P, true? And then we can even put this where we have the natural log of T2 over T1 is equal to the natural log of P2 over P1 to the power R2 over C sub P. Does that all make sense? Those algebraic manipulations? Exponentiate both sides. T2 over T1 is equal to P2 over P1 to the power R over C sub P. You recall that R is equal to C sub P minus C sub V, and that K is C sub P divided by C sub V, and you can re-express that exponent as K minus 1 over K. And here is that same equation in your equation sheet. There are restrictions. It's only applicable for isentropic process, ideal gas, assuming constant specific heats. Just like this equation, you have another equation available to you if you're interested in temperature change where you know the volume changes and it's isentropic ideal gas, or pressure if you know the volume changes. So all three of these equations are useful. Look familiar? Used them before? What's the problem that sometimes students will grab an equation like this and say, it's good for steam in the two-phase dome. It's not good for steam in the two-phase dome, right? So make sure you know the limitations of the equation. Now, if you have variable specific heat, you want to account for the variable specific heats. You still have an ideal gas, and you're undergoing an isentropic process. You must use the air tables, or you should use the air tables. Otherwise, how are you going to? There's one other way to do it, but it's a lot of work. If you have an analytic expression for C sub P as a function of temperature, you can do an integral, but it's a pain. Somebody's already done the work, put it into the air tables. So just a reminder, here is your ideal gas properties for air. So as a function of temperature, you have enthalpy, internal energy, and S naught. That's that low pressure entropy value. And then you have this extra two columns. They apply only when delta S is 0, isentropic. And you have this P sub R and V sub R parameters. And so if you're undergoing an isentropic process from maybe P1 to P2, the ratio of the actual pressures is equal to the ratio of this PR evaluated at state 2 and PR evaluated at state 1. That's how you would use this information in that column for an isentropic process. Likewise, if you're undergoing an isentropic process, how would you use V sub R? Well, V2 divided by V1 is equal to V2R divided by V1R. Do you remember that? You used that table in those two columns? Okay.